Good morning. I'd like to call the BATA Oversight Committee of Wednesday, May 8, 2013 to order.
Again, I'm Steve Heminger, Executive Director of the Bay Area Toll Authority. To my right, Malcolm Doherty, the Director of Caltrans. To my left, Andre Boutros, the Executive Director of the California Transportation Commission. The three of us are the Toll Bridge Program Oversight Committee, which has been conducting the investigation into the bolts on the new bridge. We wanted to start today with this picture, just to remind everybody why we are building this project. This, of course, is from 1989 during the Loma Prieta earthquake, which was 60 miles away and nonetheless collapsed a large deck section on the old bridge. And I must say that on the new bridge, we have faced many challenges. We are going to have to fix some bolts. We have fixed welds. We have fixed concrete. We have fixed all kinds of things in construction, all kinds of problems that we encounter. That's something you do in construction. You deal with unexpected problems and fix them. But I must say also, this picture, this old bridge, is the biggest problem we've got. And there is no fix to it other than moving traffic onto the new span. And that is why we feel such a sense of urgency to get this bolt matter resolved and to get the fixes put in place and to move traffic over to the new bridge as soon as possible. Next slide. You'll recall that at the last couple of briefings, I think we tried to organize the information we were presenting to you around three questions. We have added a fourth, which is sort of an offshoot of the third. The first question, again, what caused the bolts on the East Pier manufactured in 2008 to fail? Malcolm, again, is going to address that question and provide some new information, including a report that we are releasing today. Secondly, what retrofit strategy should be used to replace those bolts? Andre has an answer to that question, actually, today. Thirdly, I'll be dealing with the question of the remaining bolts on the East Pier that were manufactured in 2010, as well as the fourth question about the other similar bolts that are on the remainder of the self-anchored suspension bridge that are also, and again, the word we're going to use, which is just a category of material, is called A354BD galvanized bolts. That's the issue at hand. Again, that's where the East Pier is. I think you know that quite well by now. I did want to, at the outset, talk a little bit about our oversight structure because I think there have been questions raised in the public discussion about this issue about whether we have an independent review underway. And my strong belief is that we do. And this slide, I think, tries to depict that. At the top, you see the Toll Bridge Program Oversight Committee, composed of the three parties that I've just mentioned. One box down to the left, you see a peer review panel, which is independent of us. It's composed of three individuals that I'll mention in a minute, all three of whom are in the National Academy of Engineering, which is the most prestigious engineering body in the United States. To the right, to their right, you see BAMC, which is an acronym for a consulting enterprise that we have hired, we, the Bay Area Toll Authority, to deal with issues that arise in this project, and their expertise spans all kinds of fields, and we have brought in additional expertise when we need to do so. And then finally, we have a whole series of contractors who are actually implementing the work. The reason we put Caltrans in orange, that's their color after all, but to make the point that that is where Caltrans is, and everything else in this operation is not them. And so there is, as I indicate, a good deal of independence here of multiple agencies and multiple checks who are doing this work with us and making sure that we do the work right. Again, this is us. I won't dwell on this other than to say that we are a statutory mechanism that was created by the legislature in 2005 and have been dealing with issues like this, maybe not as many cameras as that, but issues like this for many years while we've been building the bridge. I mentioned the peer review panel, and I do want to mention these three individuals by name because their careers are really stellar, and they have been invaluable throughout the history of not only this project, but the Toll Bridge Seismic Retrofit Program. Frieder Sibley, who is the Dean Emeritus at UC San Diego of their School of Engineering, very well-known, world-renowned expert on long-span bridges. He's now a professor at a university in Australia. Ed Idris, who is an emeritus professor of civil engineering at UC Davis, and he's one of those guys that whenever they have an earthquake somewhere around the world, he parachutes in and figures out what happens and helps learn that information as the science of earthquake engineering advances. And the third, and especially relevant, I think, for this inquiry, is John Fisher, who's a professor emeritus of civil engineering at Lehigh University in Pennsylvania. Very, very capable man who has helped us enormously on this project because of his background in examining steel failures. And that is exactly what we had here. And he has looked at those kinds of failures in all kinds of places, including on many bridges around the world. And he was also called upon, if you'll remember, after the collapse of the World Trade Center in 2001, he was one of the experts called upon to opine about why that happened. As I mentioned, all three members of the National Academy of Engineering. And I know there have been questions raised in some media circles about whether these gentlemen are really independent because we pay for their airfare and whatever else we might do to get them out here. I can tell you from personal experience that they are not ever bashful about telling us things we don't want to hear. And that is continuing in this process as we go. I also wanted to announce today a step that we are taking in addition to all of that review to ensure that we have an independent, I'll call it a double check, on what our investigation yields in terms of findings and recommendations. And that is, we have asked the Federal Highway Administration to conduct an arm's length review of our review. And they have agreed to do so. You have at your places a letter that we have sent today to Vince Mamano, who is the division administrator, the California division administrator for the Federal Highway Administration, and we look forward to working with them. They will make whatever findings and judgments they make independent of ours, and I think that will provide a level of reassurance to you and to members of the public and the legislature and the administration that we are getting to the right answers and we are getting to the right solutions. So I will turn the presentation over to Malcolm to deal with the first question on the 2008 bolts.
Thank you, Steve, Mr. Chair, Commissioners. I again appreciate the opportunity to be here and collectively, as part of the Toll Bridge Program Oversight Committee, answer questions and provide information and an update. Again, just for clarification, this is a slide that we've talked about before, but again, specifically, I will talk about the 2008 bolts that are located at Shear Key 1 and Shear Key 2 that are highlighted on that PowerPoint presentation in red. And I think we were very descriptive about those specific bolts in the past. Again, we know what caused the failure of those bolts from 2008, and it was determined that it was hydrogen embrittlement. And we have completed well, let me go to the next slide and talk about hydrogen embrittlement just as a refresher. We talked about this as well last time. Hydrogen embrittlement requires three key components or three key elements: the susceptibility of the metal and the rods and or bolts, the presence of hydrogen in a certain quantity, and then also the tension that is imposed on those rods or bolts, and we will actually elaborate on that later in the presentation and as well. The root cause of the failure is attributed to higher than normal susceptibility of the steel to hydrogen embrittlement. This again is a detailed picture under a electron microscope of a metallurgic analysis that shows the lack of uniformity. I won't necessarily elaborate on the detailed picture, but what I do want to draw your attention to is the report, the metallurgic report that has been made available to you as of today, and the analysis that was completed. And really what I want to draw your attention to is page 12, where it talks about the conclusions and the recommendations. In summary, it talks about the metallurgical structure and substructure of the steel in these bolts, which are fundamentally a result of alloy selection and heat treatment conditions, has apparently made the rods less tough and therefore more susceptible to hydrogen embrittlement. On that page, the first conclusion is that the anchor rods failed as a result of hydrogen embrittlement, resulting from the applied tensile load and from hydrogen that was already present and available in the rod material as they were tensioned. The root cause of the failures is attributed to higher than normal susceptibility of the steel to hydrogen embrittlement. The third bullet is the metallurgical condition of the steel was found to be less than ideal. More precisely, the microstructure of the steel is inhomogeneous, resulting in large difference in hardness from center to edge, and that's what this picture represents, and high local hardness near the surface. As an additional consequence, the metallurgical condition, the material exhibits low toughness and marginal ductility, and again, we're talking about specifically the batch of bolts in SEER 1 and 2 that came in 2008. The combination of all these factors have caused the anchor rods to be susceptible to hydrogen embrittlement, which ultimately was the cause of their failure. The recommendation is that future procurement of A354 grade BD anchor rods should include a number of standard supplemental requirements to assure against hydrogen embrittlement failure. The appropriate specification of supplemental requirements is currently under review, and I think we'll talk about that a little bit later on as what we're doing with the 2010 bolts, such that it will lead us to potentially modify the amount of testing we do on this type of bolt going forward. This recaps the recommendation that I just iterated to you, and again, the conclusions of the metallurgical study are on page 12. And I also will draw your attention to the information that is on the front page that highlights the individuals that authored this report. One of them is the chair of ASTM Committee on Fasteners, and then the other two, one is a consultant, and one of them is on staff in our materials testing laboratory. The specifications, we've talked about the specifications that went into calling for the A354 BD bolts. The way that works is a technical design specification team evaluates the bridge design and selects the type of bolts for the application that was called for in the plans. The design specification team subsequently added a supplemental requirement for these bolts, blasting instead of pickling, to address the potential for hydrogen embrittlement. That is consistent with the recommendation and the cautionary note in ASTM 354 standards if you're going to galvanize those bolts. Current Caltrans bridge specifications do not allow the use of galvanized A354 bolts for standard bridge applications, but non-standard applications may be considered, and that's where we are on this project, where we have project-specific specifications. And again, ASTM does allow for galvanization, but it cautions on the potential for hydrogen embrittlement, and that refers us back to the previous bullet as to what steps you should take to avoid or lower the risk of hydrogen embrittlement. Caltrans has ordered replacement bolts for the 2010 bolts that we are subjecting to destructive testing. So not on SEER 1, SEER 2, there's another batch of bolts that came in 2010, and they are being tested out in the field in situ right now. We are also doing destructive testing to those bolts. The replacement bolts for those, we have asked for special provisions of those replacements, and it includes but is not limited to tighter requirements for hardness and additional testing to address the potential for hydrogen embrittlement, such that we do not have that experience again. And in hindsight, these are the types of requirements that we would have been well served to have on the 2008 bolts, and this is what we would look at going forward for testing in situations when we were calling for these types of bolts. With that, I will turn it over to Andre Boutros from the CTC to talk about the retrofit to the 2008 bolts that I just described that were problematic.
Thanks, Malcolm. Mr. Chair, Commissioners, Andre Boutros, Executive Director, California Transportation Commission. If you recall from the last discussion, we talked about two options that we were investigating to put the retrofit in place. The first option was called a steel collar, and just before I describe that, let me give you a little bit maybe of an orientation here to what the colors mean. The orange colors here are what we're calling the bearing assemblies. The blue, dark blue, is the shear key element that we're talking about. So that's really the element that's connected with the bolts that failed. Those are the 2008 bolts. The light blue is what's really termed here as the steel collar. That element is essentially clamping the existing shear key in place into the concrete into the concrete on top of the columns. The bolts of the existing shear key will all be abandoned. They'll be essentially taken out of the way so we can perform this retrofit. The yellow are elements that would be required to assist in that clamping force of that steel collar plate. So this was option 1. And we have another option, which is option 2, which was called steel saddle. And again, what you're seeing here is the bearing assemblies, the shear key, and then the purple is the new element, which is now referred to as the saddle, that essentially sits on top of that shear plate, a shear key plate, and that will be connected to steel cables that will be post-tensioned, and they will be essentially covered in that yellow section that you're seeing there, which will be additional concrete elements that will cover all these cables so no one can see what's there. And that will be performing the same function as, again, the original design in terms of providing the shear capacity for that shear key to resist the lateral forces. So after looking at these two options, quite a bit for several weeks now, we've analyzed the options for both constructability as well as cost, as well as pros and cons, and some of the pros and the cons are described on this slide. Option 1, in terms of pros, both options actually, the pros are that we do not mess with the shear key itself. We don't take it out to replace it or anything of that nature. For option 1, the pro is potentially it is simpler to fabricate because it is stacking steel plates on top of each other and anchoring them together and then into the concrete. As far as cons, there's a lot of steel here that would be required for that particular operation, and there will be a lot of milling and a lot of shop machining to make sure those plates are smooth and they can fit together. There's definitely more coring related to option 1 into the concrete that we are kind of concerned about in terms of potential damage to other elements of that cap beam. And then one of the cons is, of course, the cost, which is right now estimated at $15 to $20 million. As far as option 2, which is the steel saddle, again, there's no need to remove the key. There's less scoring required. It is potentially less difficult to install because most of the installation would be really external to the concrete. So we're wrapping those elements around the concrete cap. It is definitely less costly. It is $5 to $10 million. And then as far as cons are concerned, there is a special or unique saddle system that would have to be fabricated to make this all happen. After debating both options, like we said, we're recommending option 2, which is the saddle. It essentially, as would option 1, provide the clamping force that would be required to hold down the shear keys as originally designed. Again, the 2008 bolts altogether would be abandoned. They'll be taken out of the way where they conflict with the installation of the new assembly. Option 2 would require more detailed fabrication. However, installation will be less difficult, as I mentioned, and will require less coring of the concrete on top of Pier 2. It is definitely less cost. As far as the schedule is concerned, we're working with the contractor right now Caltrans is working with the contractor to make sure that this retrofit can be completed by Labor Day. We do not have an estimated time yet. This is in the negotiation process, and it'll have to be worked out in terms of a contract change order with the contractor. But we're hoping that this can be in place before the planned opening of Labor Day. And with that, I'm going to turn it over back to Mr. Heminger to describe the 2010 bolt issue.
Thank you, Andre. So the remainder of this presentation will focus on the bolts that have not broken, and that's obviously an important distinction. Here again is Malcolm's slide, but with a little more detail and a little more color. As you know, we have been learning as we're going in this investigation, and I think one place where we provided you an incomplete picture in the last couple of briefings is on the East Pier. So we want to give you a more complete picture here. We have spent most of our time briefing you on what I will call the downstairs bolts, the bolts that have been connecting the bearings and shear keys to the pier cap, and they are shown in the longer boxes that you see on this slide. The red ones, again, those are the 2008 bolts that failed that Malcolm has described to you. There are similar bolts made in 2010 in yellow. That are also downstairs bolts, and they are connecting the remaining bearings and shear keys to the pier. One difference that we have emphasized to you in the past is that the 2008 bolts in red are embedded in the pier because of their location over the column leading down to the water, whereas the yellow ones, the 2010 bolts, are not embedded. They're through bolts. They go all the way through the pier cap and have nuts at either end. What we have focused less attention on in our briefings to you, and we want to include today, are another couple of sets of bolts. The second major set of bolts are what I would call the upstairs bolts. They're the bolts that take the shear keys and bearings and anchor them to the roadbed, what we call the OBG, the orthotropic box girder. So the bearings and shear keys are in between two very large things, a concrete pier cap beneath them and a steel OBG that's above them. And as you can see here, in terms of the green areas, there are another 500 bolts, also manufactured in 2010, that connect those shear keys and bearings, the upstairs bolts, to the deck that's above it, the steel deck, and above the steel deck is the riding surface that you drive on. In addition to those, there are also an additional 400 or so bolts that are smaller. All the bolts that I've described so far are roughly 3 inches in diameter. The ones that go through the pier cap are very long. They're 15, 20 feet long. The upstairs bolts are much shorter, but they're as wide in terms of diameter because they have a very small distance to cover just to connect the bearings and shear keys to the OBG. The bolts that I'm now going to describe, the additional 432 bolts, are 1 inches in diameter. They're much smaller, and in fact they vary from 2 inches to 2 feet in length, and they are internal to the bearing assemblies, the Bs that you see on this sheet, B1, B2, B3, and B4. And so that comprises the totality of the bolts that are on the East Pier. It's about 1,200 of them. And again, manufactured in different batches, 2008, 2010, some of them of different sizes. Most of them, both the downstairs and the upstairs bolts at a fairly high tension level, and the remainder, the ones internal to the bearings, at a slightly lower tension level. And as we've discussed with you, that's a relevant fact in terms of this issue of hydrogen embrittlement, or the long-term problem, the long-term potential that we're concerned about with stress corrosion. So having that as background, what have we been doing? We have been testing these bolts, and as Malcolm indicated, we've been testing them not only on the site with some field equipment, and I think you've seen some of that testing going on in the press, which is good for the public to see it. But we've also been testing them in labs, and when you test this stuff in the lab, you break it. And so that destructive testing has been underway, and that breakage involves pulling them apart and then examining how they fail, and then cutting it up and putting it under the microscope and doing all sorts of tests to it so you know what is going on. The most important finding, of course, is out there in the field on the pier, and that is that none of these bolts have broken. And so the longer they are there not doing that, the more daylight we are seeing between the 2008 bolts, which had a hydrogen embrittlement problem that, generally speaking, this problem develops in the short term, and the 2010 bolts that do not seem to be developing this problem. The preliminary test results as well are showing them to be a more ductile or flexible material, not as hard, especially on the surface, as Malcolm indicated, which was a major culprit in the failure of the 2008 bolts. And we are not seeing any hydrogen embrittlement. That little break at the bottom, if you can see that circle there, if you remember the break that occurred on the 2008 bolts from a prior presentation, it was a brittle break, and it was fairly clean. You see here that this break is much, I won't say dirty because that's the opposite of clean, but what it reveals is something that pulls apart and is more ductile, more flexible, which is what you would like to see in this test, so that it's not as brittle, not as hard. We are also anticipating additional test results after today that will be going on for the next few weeks, and then there's another test that I'll describe that will take a little bit longer than that. Lots of numbers here, and I beg your pardon about that, but I do want to focus on two sets of numbers here, which are at the far right of this chart. I think we showed you a version of this at your last briefing, primarily concentrated on the first two rows, which are the 2008, again, downstairs bolts, and the 2010 downstairs bolts. If you move over to the right and you look at the hardness characteristic of those bolts, you'll see a difference. In other words, that the 2008s are quite a bit harder than the 2010s on average. What you will see above that is the ASTM standard, which has a range there of 31 to 39. So the higher up you are on the range, the harder you are. And then on the far right is a new test that we have been conducting. It's a toughness test, and it's called the Sharpie test. And it essentially involves taking a device that's like a pendulum and swinging it into the material and seeing what kind of toughness that material has. You basically put a notch in the material so that when you swing it, you can break it. And how far you swing it, how much you need to swing it into the material, is an indication of the toughness. And here again, you can see a significant difference between the 2008 and the 2010 bolts. This particular test, you do it at two different temperatures, because obviously steel gets more brittle when it's cold as opposed to being hot. And what you see are the values, in other words, the swing width, I'll call it. And you can see for the 2008 bolts, much lower values. For the 2010 bolts, much higher values. Now, what we've arrayed on this chart that is new information also for you, the toughness information is new, and you can see we haven't finished the toughness tests on everything, but we've also arrayed for you the hardness information as well as these other metrics that I won't dwell on in particular for the other bolts that are on the East Pier that I just described to you. And you can see, Peter, if you'll help me with the cursor again, right below the 2010 bolts, you'll see the E2 shear key bolts, and again, you will see a hardness value that is more consistent with 2010 than with 2008. And if you go down the list, you will again see values, most of them closer to 2010 than 2008. The reason we have two ASTM standard rows on this chart is because they have a different standard the bigger the bolt. So the big bolts are on the top, greater than 2.5 inches in diameter, and the smaller bolts are on the bottom. So again, the data we're seeing is showing a divergence between the 2008 bolts that failed and the 2010 bolts that have not on various elements of the pier cap. The other test that I mentioned earlier is something we're calling the wet test. And what it is it's a test that is trying to, I see some snickering going on. You'll have to stop that. We're trying to simulate a long-term phenomenon, which is stress corrosion. And I think we mentioned to you earlier that hydrogen embrittlement and stress corrosion, both of them, are time-dependent. In other words, when you do a test on a material, you don't see it in the material. You have to subject them to conditions that simulate a time-dependent failure. And in the case of the hydrogen embrittlement, as Malcolm indicated, what we're specifying for any replacement bolts is some kind of time-dependent test before you put them on the pier. For example, you take them into a lab and you put them under tension and you see if they break. We didn't do that with the 2008 bolts, and we should have in hindsight, because that would have probably shown us that if we had a problem, we had a problem in the lab instead of on the bridge after they were already included. And so that's the kind of test you need for the embrittlement question. For long-term stress corrosion, you're trying to simulate something that occurs over years or decades, and that's considerably more difficult. So we have come up with a really custom test that is going to try to simulate that longer-term susceptibility to stress corrosion. We're going to take full-size bolts off the pier from the 2010 batch, and they're going to be basically placed into a bath of a salt solution and tension progressively over a number of days until they fail. And from that test, we will be able to learn the particular susceptibility of the 2010 material to stress over time. And that will give us a lot of good information about how to deal with those bolts in the future, whether they ought to be replaced in the near term, whether they ought to be replaced in the longer term, whether we ought to reduce the tension on them if we can, given the design of the bridge. We really do think this test will really help guide what we do with these bolts in the future and over the life of this new structure. Stress corrosion, it's worth just a little bit of a digression to emphasize the importance of the metrics that I've been describing to you. And this curve is probably the best picture we've got of what you need to worry about with stress corrosion. And on the bottom axis is hardness. And again, the harder the material is, the closer that line is to, again, the line shows you two basic parts of this, fields in this graph. Below the line is good. Below the line, you have less likelihood of failure. Above the line, you have more likelihood of failure or fracture, as it's stated there. And so the axis at the bottom, the horizontal axis, is a function of hardness. The axis over there on the left, the vertical axis, is a function of two things: the tension level that the material is under and the size of the material. And size here does matter. And as you go up that scale, you have more of a problem. As you go right on the horizontal scale, you have more of a problem. So if you have a very hard material, you want to have it at fairly low tension. If you have a material at very high tension, you want to have it be not so hard. You want it not to be subject to the brittle condition that can lead to the failures. This, by the way, is from the textbook of John Fisher, who was one of our experts. So, those are the bolts on the East Pier. Again, about 1,200 of them. There are another roughly 1,000 bolts that are 354 BD galvanized on the rest of the SAS. And what have we done about those? As I think we informed you at your last meeting, we have been conducting visual inspections of those bolts for some time now on a regular basis, and they are performing as they are required. Now, it's worth noting and emphasizing, as we did last meeting, that some of the E2 bearing assembly bolts, the ones that are inside those bearings, we cannot inspect because they're in there. Now, they were observed before they were put in there, and the bearings were closed up. And we are tracking down, as we've shown you here, their quality control data. So we know quite a bit about those bearings. The one thing we can't do with the internal bearing bolts is pick apart the bearings and look at them. But we have the observations we made before. We also have the quality control information that we are assembling. And as I indicated before, and want to emphasize again, most of the bolts at the other locations off the eastern pier are at much lower tension levels, and that is a very significant difference that they exhibit from the others. And in fact, here is a roster of them all, and working your way from top to bottom, you'll see the first several sets are the E2 bolts on the east pier, and then you have some inside the anchorage, which is toward the eastern end of the bridge, some at the top and the bottom of the tower, the suspension tower, some in the east saddle, some in the east cable, some in the west pier, where there is also a saddle. Even the bikers get their own anchor rods. Everybody gets anchor rods on this bridge. And the relevant characteristics for you to look at on this chart we've depicted. First of all, the diameter. And the bigger they are, the more difficult they are to manufacture, and also the higher up they go on that chart that I showed you in terms of stress corrosion potential. Length is not as important, although, you know, the longer they are, that's a bit of a manufacturing challenge, but not as operative as the diameter. You can see the quantities depicted here, and it adds up to about 2,300 bolts on the SAS. Again, this is contained to the self-anchored suspension bridge, the steel element of the bridge. The vast majority of the length of the new bridge is a concrete skyway, no bolts. And finally, and we've highlighted this in purple, that's the tension. And as you can see, it's a fraction of FU. FU is not what you think it means. It's its ultimate capacity. In other words, when it would fail. And you can see that on the east pier, we've arrayed these from roughly more tension to less tension. On the east pier is where we have the highest tension levels, which is why this issue, we have focused so much of our attention on the east pier. As you head down the chart, you see much, much lower tension levels, in some cases what we would call snug tight, just as you would snug up a bolt anywhere in your garage. Next one, Peter. As part of our investigation, we have also asked Caltrans to review the other toll bridges in the Bay Area and whether or not they have used any of these 354 BD galvanized bolts, either in new construction or in the retrofit program that we've had underway. And Caltrans has identified one location where they were used on the Richmond-San Rafael Bridge retrofit. Caltrans has been inspecting that area on that bridge for some time, and so has records, and they also went out and did some visual inspections over the weekend. We have observed no performance issues. There are a couple of very important points to make about the Richmond Bridge bolts. The first is they were installed well before the bolts that we're talking about here on the SAS. We are going to track down their quality control records and the like, but we're not certain where they were manufactured, but they were put in well before these bolts at issue. I think the most important difference is they are also snug tight. They are not under any real tension load at all, and that tension is really what matters in terms of near-term embrittlement, which they do not exhibit, as well as long-term stress corrosion potential, which they should have a very low susceptibility to. But we are going to do our due diligence on these, just as we're doing on the SAS, just to track down the quality control and continue inspections to make sure we're okay. So, what's left? We do appreciate your indulgence in us sort of barging into your meetings every couple of weeks, and we're going to have to do it at least one more time. And I appreciate that Chair Worth has agreed to call a special meeting of the Bay Area Toll Authority at the end of the month, so we won't be barging into a regular agenda. We'll be on our own by ourselves. And at the May 29th meeting, which is when it will be scheduled, we believe we will be able to give you a decision on the 2010 bolts, because we will have all the relevant test information we need, with the exception of the wet test. And the wet test is something that we can use to gauge our behavior going forward. It's not something we think we need immediately to make a decision necessarily about what to do about the 2010 bolt locations, especially on Pier E2. And we will have also completed all the document review that we need, not only for the bids, the 2 bids that were conducted to build this bridge, but all the quality control information that was provided. If I could, in closing, just draw your attention again to that letter from the Federal Highway Administration, because I think it gives you 3 helpful categories into which we believe we will be classifying the bolts on the SAS in terms of our future activities on inspecting and repairing them. The first category we intend to classify bolts into is bolts that are to be replaced before opening the bridge to traffic. And we already know that the 2008 bolts fall into that category. We do not know yet whether any other sets of bolts fall into that category, but we will be able to tell you that, I believe, on May 29th. Secondly is a category of bolts that are to be replaced after opening the new bridge to traffic as a precautionary measure to avoid premature failure due to stress corrosion. So what that means is we may decide to replace some bolts that haven't broken, but we may decide to do it as a precaution to avoid a concern about stress corrosion in the future. And finally, there will be bolts we expect, and we expect the vast majority of them will probably be in this category, that are to undergo a regular inspection schedule and only be replaced as necessary if damage is observed in routine use. And one helpful way, I think, of starting to think about how we might differentiate is between the bolts that are on the East Pier under high tension and the remainder of the bolts on the bridge. That is the drift of the data that we have received to date, but we do not have all of it yet, and so do not want to make that judgment until we do. And so again, Mr. Chairman, that concludes our presentation. We appreciate your patience, and we're available to answer your questions.
Thank you, Steve, Malcolm, and Andre. Appreciate that report. We're going to start off with Commissioner Campos.
I don't know if the chair wants to start.
Well, I just had a couple of quick questions.
Yeah, I didn't.
Either one? Okay.
You're the chair.
Oh, thank you, sir. I have several, but if I could just start with a couple of them. I just wanted to clarify this option to steel saddle and try to kind of reconcile it with another photograph that we got initially. And it shows the 2008 bolts that have failed, and then it shows the 2010 bolts on either side. So is it clear to say that this option to steel saddle, the 2010 bolts would continue to be in that system? And basically what this does merely is replace those 2008. So we have to visualize the other ones also in it.
The 2008 bolts will be abandoned, so essentially we will not be counting any capacity of any of the bolts, so ignoring them altogether. Some of them will be cut on top at their connection on top of the plate to allow for the saddle to ride the plate essentially, so it can sit on top of the plate and hold the plate down. We're not taking them out of the concrete because there's really no point of doing that. We may be causing more damage to the concrete, trying to get them out because they are embedded. We can't get to them from underneath. They're essentially anchored on top of the bearing assembly and they're anchored at the bottom of the concrete, so we can get to them from either end.
Okay, so okay. And I guess the other thing, I wonder if you appreciate the information on the retrofit. Can you talk a little bit more about the process that you went through and tie this within, for example, we've got these, we've got additional experts on our, that Steve identified in terms of giving us a perspective on this. Can you talk in a little bit more detail about how the design process went and how the independent experts weighed in on helping come to the conclusion that this was the best
Sure.
way to go?
Let me start, and maybe Malcolm, you can. Essentially, the design engineers, which is T.Y. Lin International, as well as assistance and feedback from the contractor, and Caltrans, of course, a lot of the engineers in Caltrans that are performing oversight on top of this have determined that any assembly that will be put in place will have to resist the same loads that this structure will be subjected to regardless. So that was really the starting point, and that's what we need to keep in mind, that we're not really diminishing any capacity or any intended behavior of this bridge by this retrofit. This retrofit will provide the same design capacity that was intended. So that was really the first thing. And designing shear keys is essentially really taking a deflection, a movement of the bridge into account. So you're limiting the movement of the bridge by putting this shear key in place. So there are allowances that the design had put into place when the original design was put in. So those same allowances came into play. And I may defer it to Malcolm here because this is really getting a little bit more technical for me at this point.
Both alternatives were designed to a 65% design stage such that we had enough information to make a decision on the pros and cons and which one to move forward. As Andre pointed out, our consultant of record, T.Y. Lin, as well as Caltrans engineers were involved, and then both alternatives were also provided to our peer review panel to comment on both of them and offer up information to the TBPOC before a decision was made on which alternative was the best one to move forward with. But both of them provide the functionality that we need.
So, and I guess to final question on that, so it sounds like there was kind of complete concurrence that by everybody we talked to, including the independent review panel, that this option was the best way to go in terms of protecting the integrity of the existing structure but providing the work that we needed.
Absolutely.
That is correct.
Yeah,
Okay.
absolutely.
Okay.
And really, just to give you more assurances from our standpoint as the POC here, we would not be presenting the solution to you if it weren't providing the solution that will provide for that safety, for that intended design, for that behavior of that bridge.
What I think we just want to understand is kind of what the process is when you go back to design an element, so that who's weighing in on it, who's
Right.
reviewing it, and that kind of thing. So, and I have one other question, and we can take the answer now or later after we focus on this. But I wanted to see, one of the other things that has come out over the last week are questions about the welds in the tower. So I don't know if you want to answer that now or prefer to handle the remaining parts of the report, the presentation, and then go back, whatever is best.
If it's
Go
your
ahead.
pleasure to answer it now, I'd like to call Brian Maroney up to the podium. Brian, I think at least Commissioner Sparing will remember Brian because he's been with us from the get-go on this project, and he is our go-to guy on this bridge. And in fact was one of the folks who were instrumental in persuading the governor at the time to build a new bridge. And I'm sure there are days when he regrets that like I do, but it was the right decision. And Brian has been involved in all the major innovations of the bridge. And this welding, in fact, is one of those innovations.
Commissioners, thank you for, good morning. Thank you for letting me have an opportunity to talk about that. With respect to your question, I guess I'll just start off with the self-anchored suspension bridge literally has miles and miles and miles of weld in the tower, in the deck, just all different types of welds. Contractors will select a type of weld based on what's going to be best for that particular type of weld. And it might be because it's flat, it might be because it's going up and down vertical, it might be because it's overhead, it might be because of its size, or the weld material that a contractor will have to melt as they connect pieces of steel together. The base of the towers, you're probably referring to the electroslag welding, is that right? That is one of many different types of welds on this job. Well, the tower, if I can paint a little picture here, tower is basically 4 different tower legs, and that's where all the self-weight is supported, and that's where all the live load, and we call live load things like trucks and cranes and cars and bicycle pedestrian weights. So the tower, 4 tower legs, they carry those kinds of loads. We call them service loads. Now, in the event of a large earthquake down at the very bottom, and again, these 4 tower legs are about 500 feet tall, round numbers. Well, the bottom, about 30 feet or so, the tower legs are connected with shear plates. These shear plates are on the order of about 4 inches thick. They vary slightly. Okay? And on every weld, on every bridge I've ever worked on, when you lay down miles and miles and miles of weld, we, by contract, force the contractor to do their own inspection. We call that quality control. Now, we have experience. We know that that's not even enough. Then we have our own people, our own inspectors, qualified, and we have our own equipment. We bring in our own equipment, and we re-inspect those to various degrees depending on the geometry, the type of weld, its function of weld, following American Society of AWS Bridge D15 code, the welding code. And then we do that. Well, when you perform miles and miles of weld, and then you necessarily inspect it, we inspect it because we know there is no mile of weld that's perfect. There are always imperfections. Now, those imperfections, some of them need to be cut out and repaired. Others are imperfections that have no consequence whatsoever to the performance of the bridge. So, like, for example, when you fly an airplane, okay, there might be a small imperfection in the wings, and it doesn't stop the airplane from very safely, successfully flying from San Francisco to New York and back. Okay, so with respect to those welds, we have found some imperfections due to that inspection, the contractor's inspectors, and our own independent. We currently have mapped 3-dimensionally out the imperfections, and some of them we've already communicated with the contractor. These are going out. Please remove them, and then we'll follow up and inspect them again. Even if we have to tear them out and fix them and inspect them again, if we have to do that 3 times, we'll do it 3 times. We'll do it, and when we leave, they will be fine. Now, there will be some that we evaluate, we agree, consensus that, yes, this is an imperfection, but it has no consequence whatsoever to the performance, and we're in the process of doing that now. And it's just, quite frankly, it's a very large weld. It's a very exciting type of weld, electroslag welding. Federal FHWA has been investing for about 15 years up at Portland State research, and many states do allow it. And we're excited to see this kind of technology coming to here in the state of California. And when we leave, this weld will be just fine. But we're in the process of doing what we do. We've probably been working on it for about, I'd say, 9 months. Are there any follow-up questions?
Chairman?
So basically, we have the 4 towers that you mentioned, and having been out there, I saw the way it comes down. When they were originally put in, there were just 2 of those shear plates, because then you had to install the rest of the towers. And then, are the shear plates installed around, and then those are basically welded together? Is that kind of?
The legs,
Right.
the 5-sided legs,
Right.
each one of them, they were fabricated and lifted and brought in. And then additional plates were brought in, and they're not service levels. They're only there for large seismic events. And then
Got
we
it.
basically connect all the 4 tower
Yep.
legs with these shear plates down at the bottom 30 feet.
Right, okay, great, thank you. Thank you very much.
I should also add that I've actually brought out the external independent peer review panel, and
Okay.
they've actually been out there more than once. They have, they review our weekly notes and progress on this.
Great.
I've taken them out there. I've actually given them demonstrations on how the inspection technologies that we use, so it's fully, fully vetted.
Thank you.
Commissioner Campos?
Thank you, Mr. Chairman. I want to begin by thanking the Oversight Committee and the staff of all the different agencies, including the MTC staff, for all the time that has been spent on this item. I also want to thank the chair of the MTC. It's very clear to me that the MTC is playing a very important role in making sure that there is transparency and accountability with respect to where we are here. So I want to thank our chair. I want to thank our executive director. I'm very proud of that role. To paraphrase the governor, to use the exact words, stuff happens. And I think that when stuff happens, it is really important for us to be very transparent and forthcoming in the information. I have to say, and I can only speak for myself, one of the things that's frustrating about this process is that I feel that we have actually gotten more information from the press in terms of some of the things that have happened than from this process. And I actually want to thank the press, whether it's Mateer Ross or Mr. Vanderbeek, and I think they have done a great deal of service to the public in terms of airing out where we are. In the East Bay as well. I'm sorry, the Times as well. My apologies. Didn't want to leave anyone out. But the first time that this was presented to us, the impression that I got, and maybe it was just my misunderstanding of how Caltrans was talking about it, it was described as sort of maybe a manufacturing issue, and the way in which these bolts were manufactured, and maybe that's in the end part of the issue. But there was no discussion about how these bolts were selected to begin with. And I know you were talking about the wet test. I have a very simple mind. I'm not an engineer. I follow the smell test. And what doesn't, to me, pass the smell test is how it is that Caltrans chose these bolts. And so I want to ask Caltrans a little bit more about that. What is the difference between an A354 BD bolt and an A490 bolt? Let's begin with that.
Okay, well, I appreciate the question and the opportunity. I don't know that we've varied substantially from the initial assessment that it's a materials issue. Whether or not the materials issue and the susceptibility and the hydrogen embrittlement was borne out in the processing or why it was in the field, I think that is kind of captured in the metallurgic report as best it can. The difference between a 354BD and a 490 has to do with the size of the bolt. When they go to ASTM standards, and I can actually talk about a 354BC, it may also help. A 490 bolt is a bolt that is limited in its length. It is also limited in its diameter, and it also has a hex nut at one end of it. A A354BD bolt is for bolts or anchor rods that are larger than 2.5 inches in diameter. They are similar, a 490 and an A354, in the strength requirements and some of the tensile requirements and those types of things, but they are different in size and magnitude. So that's one difference. A difference between an A354BD and an A354BC is the tensile strength that the two different steel anchor rods have. So you get yourself into a point where you're trying to decide how much tensile strength you need, what size it is, what function it's going to serve, and then it fits into a different category of a bolt type. But these are not 490 bolts because 490 bolts are limited in size, length, and diameter.
I understand that. So with the 490 bolts, are 490 bolts allowed to be used in these kinds of bridges?
Sure. In the right application, the right size, the right specifications, if those specifications met the application, sure.
And is there a limitation in terms of that use? Are there things that they're not allowed to be used for?
There are differences in the specs. I think 490 bolts aren't allowed to be galvanized.
Okay. And they're not allowed to be galvanized because?
Those specifications are lined out in ASTM. I think there is a concern about hydrogen embrittlement, but I don't know what other factors led to the direction in ASTM not to galvanize 490 bolts.
Given that there are some similarities between the two types of bolts, and you're talking about the 490 bolts not being allowed to be galvanized, did that raise any red flags for Caltrans in terms of moving forward with the use of the A354BD bolts?
I think it certainly, and our specifications called out special procedures to be followed with the use of the A354BD bolts. But I don't know that that was brought to our attention by the 490 specifications. It was brought to our attention by the 354BD specifications that have a cautionary note about galvanization and actually have a process outlined if you are going to use these and galvanize them, what steps to take. Another difference, going back to 354BC bolts, which are a lower tensile strength, there are no restrictions on galvanizing those bolts.
Now, in your presentation, you say that current Caltrans bridge specifications do not allow the use of galvanized A354 bolts for standard bridge applications. But then it says that it is allowed for non-standard applications. Can you explain the difference?
Our standard direction to our bridge designers is not to galvanize 354 bolts, because if you are, you have to be very thoughtful about it. It is within ASTM standards, but our standard direction to bridge designers, as a basic principle, is to not galvanize 354 bolts unless you do due care and add special provisions, which we did in this case. It's not uncommon to have to vary from standard specifications, and that's what was done in here. And it's very common to have specific specifications for an individual project.
I guess, not being an engineer, I don't understand how it is that you would deviate from the standard specifications that you have. If generally you're saying you should not be galvanizing these bolts, why would you do that with respect to this project?
Our standards also tell us not to have less than 8-foot shoulders on a 2-lane highway, or not to have less than 10-foot shoulders on a freeway. But we do in certain circumstances, and we are very thoughtful about when we do that. It's not that much different in a technical application. You have to stay, consistent with ASTM, I think would be a good rule of thumb. But we vary from our specifications whether or not it's, regarding bolts, whether or not it's regarding geometry. But you have to be thoughtful about it when you vary from the specifications. When we did that in this case, we were within the ASTM requirements, and we added what they called out to do if you were going to galvanize these type of bolts.
And what does it mean to be thoughtful? I mean, I'm still trying to, so let's say that you're going to deviate from your standards, you're going to galvanize these bolts. What is that Caltrans requires in terms of being thoughtful when you're deviating from their own standard?
I think back on slide 14, it described a couple of bullets that talked about the technical design specification team evaluating the bridge design and the specifications. So there would have been thorough conversations about what specifications to use. And there should be documentation going into what the logic was to vary from those specifications.
Is the wet testing that was talked about, is that part of the process of being thoughtful, that's something that you want to do?
Well, let me add to this, and then Steve may also, let me answer it, and Steve may want to add to this as well. One of the things that I think that is very apparent is when we're ordering the replacement bolts for the 2010, we have put a lot tighter specifications and a lot more testing requirements on those replacements. And in retrospect, that would have served us very well to have those same tighter specifications as far as additional testing when we called for the A354 BD bolts to be galvanized.
Commissioner, if I could, the wet test is something that we are essentially inventing, and it's trying to deal and simulate this issue of long-term stress corrosion. I think the more relevant concern here is the short-term hydrogen embrittlement problem. And at least in my mind, there's no question that if we had specified with the 2008 bolts that we do a time-dependent test in the lab before we put them in the bridge, we would have been a lot better off, because I think it's likely they would have failed in that test, and we wouldn't have installed them on the bridge. And the complicating factor, as you know, is we installed them in a location where we basically couldn't get them out again. So that, in addition, I think should have cautioned the folks at the time to say, geez, if we can't get these things out again, shouldn't we test them off the bridge before we put them in? And so that is, I think, one of the clear lessons learned, and it's on the slide that, looking back, I think, as Malcolm indicated, the process, and we have yet to get all the documents in front of us so we can actually look at the minutes of the meetings, what was discussed, what happened. But once we have that, I think the question really is, they clearly were aware of the issue because the prohibition on pickling was included in the specs. But we think there should have been more included in those specifications, which is why we're doing so in the replacement bolts that we're ordering.
Just following up on to Caltrans, so you deviated from your specifications in terms of the galvanizing of these bolts, of the A354 bolts. Is there any other area in the construction of this bridge where Caltrans deviated from its own specifications?
I'd have to
actually defer to Brian Maroney and the design team, which included our consultants. From a technical standpoint, from a geometric standpoint, I don't know that I can answer that question definitively without going back to the design team.
And I think that's part of the concern here, that we see, based on what happened, what does occur when you in fact go down the path of deviating from your own specifications and some of the challenges that come with that. And so I think it's fair for us to ask, if it happened with respect to these bolts, where else, with respect to the construction of the bridge, did it happen?
Commissioner, if you'd like Brian Maroney to try to address that.
Thank you.
I'm sure he could.
In 25 years as a bridge engineer, I've never worked on a project in design or construction where we didn't have something we call special provisions. Think of a package for a plan for a bridge. There are a bunch of plans, and those are the drawings. And then there are the specifications, and those are kind of like the directions, how you do it, what you can do, what you cannot do. And there's two types of those directions. One are the standard specifications, and it's a book that we use, and it's hundreds of pages long. But every single project has something what we call special provisions. And it's because those standards don't really fit. And you have to come up with an engineering technical solution to how you still get the performance of the bridge structure that you need. The Bay Bridge, like every other bridge, has many special provisions, or many special deviations away from the standard. Like, for example, let me give you a simple one. As you come out of the tunnel, the roadway on the west spans of the Bay Bridge, the roadway in the tunnel, okay, it does not meet our standards. It doesn't. And the brand new bridge that is on Yerba Buena Island, as it transitions to the brand new self-anchored suspension bridge and the skyway structure, that brand new bridge, it also doesn't meet those full lanes because it's connected to substandard lanes, and then it transitions out to larger ones. The super elevation is the same way. I personally was involved in one such deviation. Caltrans standards at the time of the design of this bridge was to use something called maximum credible events. And that sounds like a very interesting term and a confidence-building term, maximum credible event. But as a bridge engineer and somebody who specializes in earthquake engineering, I can tell you the maximum credible earthquake motions can be exceeded. They are a statistical, characterized set of ground motions. I, quite frankly, led or drove a variation to use probabilistic motions, 1,500-year return probabilistic motions. A typical building in San Francisco is designed for about a 500-year return period motion. Outside of California, AASHTO has fully adopted probabilistics, 1,000-year return period motions. Here we're using 1,500. Now, how did I make sure that this was an improvement? First of all, I augmented the team with specialists in this area, people like Bruce Bolt, people like Norm Abrahamson, people like Joe Penzine. These are the people who design the ground motions for nuclear power plants here in California. These are the people who design the ground motions for things like dams in Southern California. These are the people who design the ground motions for Yucca Mountain, where the world keeps the most nasty things. When I develop it with the proper skilled professionals on every single one of them, then I have to vet it out through my external independent group. So typically, at least when I'm involved in it, I'll develop it with the folks that have the proper background, and then I'll elevate that to my external independent peer review panel on ground motions. So there are many of them, and every job is like that.
Well, thank you. I just have a couple of final questions, and I guess one would be for Steve. Steve, I actually think it's a great idea that this letter was written to the Federal Highway Administration, and I guess the question that I have is, in terms of ensuring the safety of the bridge, who has the final say, and what role will the federal government have in sort of the technical guidance on that issue?
Well, under the statute, this committee, you're looking at the three of us, have been overseeing the project, and we have selected the retrofit solution you've seen, and we're going to proceed with it, as we proceeded with many things. Now, at some point, as I indicated in this letter, you need to make a call about which bolts fall into which categories. And I think the most important distinction is between the bolts that you might want to replace before you open the bridge and the bolts that you might want to replace or monitor after you open the bridge. And we've already made the call on the 2008 bolts, and I don't think there's any debate about that. We can't open the bridge without them because we need those shear keys to be operational. I think there may be a debate about whether other bolts should be replaced before or after. And I think the operative question there goes back to the picture at the beginning of this presentation. Do you want to have people traveling on a bridge you know is unsafe in the event of a major earthquake while you replace bolts on the new bridge that haven't broken? I'm not sure you want to say that is your answer. But it's a debatable question. And I think we're dealing here with not only engineering concerns, but public confidence. And I think that public confidence has taken a beating over the last few weeks. So we are mindful of that. To answer your question directly, we are asking for the Federal Highway Administration to bring their expertise to bear, that once we make a judgment on 1, 2, and 3 in this letter, we want to see if they concur. If they do, then I think ultimately this bridge is owned by the state of California, and the head of the state of California is the governor. I think his office will eventually make whatever call needs to be made about opening the structure. We will advise the administration when we believe it's ready, but I think that will ultimately be a judgment of elected officials, as it should be. If the Federal Highway Administration doesn't agree, then we've got a new problem, and we'll have to go through that. But the purpose of an independent check is not to necessarily get an answer that says you're right. It's to be willing to be told that you're wrong or that there's another way of looking at the issue, and we're willing to do that.
I think that makes sense. I think having that independent judgment is important. Last question. Given where we are right now, given that we're talking about this federal agency also coming in, what does it look like in terms of the opening of the East Pan?
Well, you'll notice, Commissioner, in the presentation we didn't give you any guarantees, so I'm not going to give it to you orally either. We do believe when you look at the volume of work that needs to be done for the retrofit of the 2008 bolts, that work can get done by Labor Day. Now, it will probably involve extra shifts and perhaps even 24-hour-a-day operation, and that will tend to cost you more money. So on that question, we do need more work with the contractor, as Andre indicated, and we're not going to be comfortable giving you a forecast on that, I don't think, until the end of the month. I think the wild card, again, is whether or not there needs to be any other work done before we open the bridge. And again, we hope to give you our best sense of that at the end of the month, because especially on the East Pier, we need to make a call about the remaining bolts on that pier, as Chair Worth was driving at. Do we need to replace those 2010s right next to the 2008s now, or can we replace them later, or do we watch them for a while and decide at some future point to replace them? This bridge, as soon as it opens, it goes into a maintenance program, and we've got some early candidates for a lot of attention during that maintenance program, and it's all these bolts.
Thank you very much.
It's just a general question. It's been on my mind since this started, this process started, and it's admittedly comes from my upbringing as a farmer and being around people who were involved in building heavy equipment and doing an awful lot of welding. Besides the enemies of welds and bolts that we've heard about here, the one that I learned about as a youth was vibration. And I'm just wondering, we haven't heard much of anything about that. If we're satisfied that vibration itself isn't, part of the causation of what's happening out there. I'm not dissatisfied with those things that have been pointed to by the investigation thus far as part of the problem. And ultimately, I suppose if you replace bad bolts with good bolts and flawed welds with good welds, somehow you're taking that into account. But I just want to be reassured that whatever engineering has been done, it's taken in the tremendous amount of vibration on that bridge.
As far as the welds go, as far as the bolts go, If we do not have a hydrogen embrittlement problem with the bolts, for example, if we don't have a long-term corrosion problem with the bolts, which is exactly what we're evaluating now, we have taken into consideration the vibrations of live load and the vibrations of wind and weather into the design of the bridge. That is absolutely an important component of the design of the bridge. We have to make sure that we have the components that are going to perform as we designed them. And I think that's what we're trying to get to the bottom of. The 2008s are already out. The evaluation continues on the others. But once we determine that they're going to function as we requested them to or required them to, they will absolutely take into consideration vibrations of live loads, winds, and everything else.
Yeah, and Commissioner, if I could mention, I asked a very similar question of John Fisher at one of our workshops, and that was his answer, that the stress loading is far more important than any of the other live load conditions that you might encounter.
Okay, I appreciate the response. I just wanted that reassurance that that discussion, that analysis has been going on. I'm sure a lot of other things have been looked at that you haven't had time to present here, but that was the one I was interested in. The other question I have, if I may, is I'm leaning toward a comfort level, personally, as one commissioner here, with regard to those bolts that are performing, that haven't failed or have shown no signs of failure or expectations of failure, to deal with them through this rigorous ongoing maintenance type of a process. And it sounds like we're going to hear more about that option later, not today. The one question I'd have is, how do you deal with the ones that you described as being embedded in the bearings that you can't pick apart? I mean, it seems to me if you can't pick them apart, you can't see them. Ongoing maintenance and ongoing testing, is still sort of the fly in the ointment.
Commissioner, you're right. And one thing is, we don't have the full pedigree on those bearings yet in terms of their manufacturing history. And that's, as you recall, what we've been doing on all the other bolts. So we want to advance that practice and that base of information so we have it. You'll recall that Malcolm brought a couple of phone books to one of your briefings that we had assembled on the 2008 bolts. And so we want to review that information on these bearing assemblies. Secondly, again, they are considerably smaller in there. They are at slightly lower tension, and they were observed before they were put together. So we again have that sense of assurance that we did not have such an immediate problem. I think what you probably do over the long run, and I think this bears some further thought on our part, but what you probably do over the long run is just, again, observe the performance of those bearings. The bearings do have an everyday use, as the steel expands and contracts. They're there to make sure that that's occurring. And at some point, clearly, if you had sufficient failure inside the bearing, you would be observing that they're not performing as they ought to. And at that point, you might need to tear one apart and inspect and do repair.
I think the only thing I would add to that is not only do we go back and look at the material and the testing and the observation we had in the installation, we would go back and look at the risk that we were facing. Many of those bolts are snug plus a quarter turn, so the tension or the stress that we're going to put those under is just not going to be in the same category where we're concerned about susceptibility. That will be another thing we look at when we talk about all those bolts.
It sounds like the plan may be to test the bearing rather than the bolt and see if there's problems there. It would just be interesting to hear a little more detail later about what that test will actually look like, so we can explain it to constituents and others that are asking us about
We'll
these
get back
things.
to you on that one.
I'd say if we can't make it by Labor Day, we should pick Thanksgiving, because we're all going to have a lot to be grateful for once this is over. So that's an unofficial recommendation, by the way. So.
Commissioner Spearing, see if you can top that.
Thank you, Mr. Chairman. I just want to commend the staff for the process that's been put in place. There was a little criticism about we haven't been forthright with the information. We really don't have the luxury of speculating and making premature announcements, and I think the staff has been very responsible going through a process of testing and analyzing what is the problem. And I think we have to appreciate that, and that does take time. And the development of this solution, it's clear it has to be vetted, it has to have peer review. These things take time, and I know there's a frustration on the part of the press, and much of the stuff we've read has been speculation, and we just don't have that luxury. And I just wanted to commend the staff that I appreciate what you're doing is the right process. I think it's been vetted. I think it's under complete sunshine. And, from my perspective, I think it's been done in a very responsible way, and I want to thank the staff. And if it takes additional time, so be it. I think it's important we take the time to find out what caused the problem, and this is the right solution. So I commend the staff.
I'd like to associate my comments with Commissioner Spearing. Well done. Anybody else?
I'm just gonna, so
Commissioner
I
Kwan?
understand that basically just this one sentence, that it sounds like on May 29th, we'll decide whether we can make the Labor Day holiday or not.
I'm going to say I hope so.
I think that if we can't decide then, that we really then have to start discussing alternative dates.
And look, maybe I could just take the opportunity, because I know there's some concern publicly that, Labor Day is important because there's a party associated with it. Labor Day is important because it's a long weekend. And I think you're aware we have used several long weekends to do very important construction work on this project. And this one, we probably need not 3 days. We may need 4, we may need 5. Because we are tying this new bridge into where the old bridge is. And so it's not just restriping and moving some cones around. There's heavy construction work that needs to occur. And so that's why we have targeted Labor Day. Personally, I wish it could have been 2 Labor Days ago, because the urgency, again, with that picture, is to get traffic onto this new bridge. So as I think Commissioner Spearing and the chairman indicated, we are working as quickly as we can, but we need to be deliberate, and that's why I want to tell you I hope so, and not promise it.
Commissioner Glover.
Let me be very clear as one member of this body, is that what I'm looking for is a safe bridge. So if the timing is not Labor Day, that date is not important to me or to the constituents in which we serve, but that we have a safe bridge to go across. And so I just want to say, as one member of this body, that when you're doing your work, be deliberate, but not to cut corners in order to meet a date.
Commissioner Worth?
Yeah, I just wanted to echo the thanks to our staff and also to the commissioners for your willingness to have a special meeting at the end of the month to go over this, and really the thoughtful questions that we're asking, and much of it is we're lay people like the public, so that we can all collectively understand both the source of the problem and the recommended solution. And I appreciate the fact that each meeting we come to, we get more material. And I think that reflects the seriousness with which the commission is taking this, as well as staff, in terms of conveying the information. So I think the other thing that's important to remember from the standpoint of some of the questions that came during the day, the next steps for the May 29th meeting focus on some of the issues about schedule and documentation. And again, I appreciate your deliberate kind of sense of really doing the homework before, in order to really provide thorough and thoughtful answers to the questions. So thank you very, very much, and thank you to everybody for their ongoing work on this. Thank you.
All right. Last speaker on this is Commissioner Bates.
Thank you very much. I just want to say I really appreciate the fact that we're seeking the independent review, and I think that's really assuring for the public, and I want to thank the staff and people for doing that, because I think that's the real issue. People need to know that we're not doing this just to get it done. We're going to do it right, we're going to do it on time maybe, and if we don't do it on time, it's not a big problem. We can do it later. But as Commissioner Glover said, it's not a question of time, it's a question of getting it right. So thank you.
Very good. Thank you all very much for being here today. We have one, I don't have any speaker cards for public comment. I don't see any members of the public coming forward. So with that, that concludes the business before the BATA Oversight Committee, and the next meeting will be June 12th, 2013 at 9:30.